All right, thanks, Matthew. Is the audio good? Okay, so it's nice to be the first talk of the entire workshop because the bar is pretty low. Right, so this is a joint work with Aaron Shine, Xander Schofield, Mingyuan Zhou, and Hannah Wallach. For the majority of the stuff I'm going to talk about, Aaron Shine is the main contributor who's awesome and taught me a lot of the Bayesian magic. And I'm going to briefly mention a follow-up work in which Xander is really the driving force for making some of the inference methods more scalable and practical. All right. So before I started my faculty position, I was spending some time at Microsoft Research. This project kind of started with a conversation with Aaron Shine and Hannah Wallach. They're experts in computational social science. It's really another form of data science. What they like to think about is apply some of the statistical tools and machine learning techniques to discover latent structure of human interaction. Okay, so what does that mean? The kind of question they like to think about is, for example, what are the main topics people are talking about? Okay, it could be, what foreign policy is, talking about among countries. Is it about warfare? Is it about finance? Or it could be, some software providers thinking about, what are the customers talking about? What are the questions they like to think about? Or within the company, what are the majority of the interaction happening between teams? Okay. So in this kind of question or, this kind of problems you would like to think about, there's one common feature, which is, the data would like to look at often take the form of counts. Okay, so this is usually some form of count data. Okay, so in terms of text, you can think of it as count of words. Okay, so the back of words model is modeling documents as a word count vector which specify how many times each word appear. Okay, and you can also think about networks, which is about pairs of actors within network and how many times they talk to each other. And you can also talk about event logs, how many times a pair of events or a set of events co-occur at the same time. Okay, so the high-level goal of this project is we would like to think about whether we can use statistical models for this form of count data, okay, while preserving privacy of the actors participating in this kind of interactions, okay, and which generates this kind of data. All right, so a very broad family of models that capture many of the count models you would like to think about. It's called Bayesian Poisson Factorization model. Okay, so this name may not be familiar with you, but some of the special cases you might have heard of. Okay, so you might have heard of topic modeling or LDA as a method of discover topic models within a text corpus. You might have heard of stochastic block models, which is a way to discover communities within a large network. And there's other examples such as population models for genetic data and many others. Okay, so in this talk, mostly we'll think about the first two examples, but this is a general technique. Okay, so let me delve into what Bayesian Poisson factorization actually look like. Okay, so in the most general sense, you have some observable countable events. Okay, usually this kind of collection of count statistics is organized into some kind of matrices. Okay, and what you would like to think about is, because these are counts, a very common way to model counts as a random variable is think of it being drawn from some Poisson distribution with unknown mean. Okay, so and what we would like to learn is the structure of the mean within this matrix. Okay, and would like to think about even though this could be a very large matrix. There's some nice low-dimensional latent structure within the matrix that we would like to discover. So in some sense, if I give you the actual unknown matrix of means, you will be able to factorize it into summary matrices of low rank. Okay, so let me give you some concrete examples of how you should think about some of the examples. Okay, so suppose you're looking at a social network and there are end users talking to different set of end users, same set of end users. Okay, so you can think about number of times any pair of users interact as some kind of count generated from some Poisson distribution. Okay, and What I would like to understand is, how are the user partitioned into different sets of communities? Okay. So one way to think about this question is, we would like to factorize this large matrix into basically 3 matrices, 2 of which are the same. Okay. So the long matrix is basically what we like to call the user community likelihood. Okay. So given the set of communities, each user basically have different weights over different communities. Okay. And we're going to put the long matrix on 2 sides, and we're going to multiply it with the small square matrices of k by k, given k communities. And this is sometimes called the inter-community likelihood. Okay, so in model, how often actors from 2 communities talk to each other. Okay, so that when you multiply all of the matrices together, that fully specify how end users talk to each other overall. Okay, so here's another example. We would like to think about topic models coming from text corpus. Okay, so here the matrix is a little different. Okay, this is a documents by words matrix. You can think about each row of the matrix correspond to a word count vector. Okay, so given document, I would like to specify how many times each word has appeared in the document. Okay, and again, I'm going to think about the number of times a word appeared is drawn from this Poisson distribution with unknown mean, and we'd like to factorize this unknown matrix into 2 matrices. Okay, the first matrix is about document topic parameters. Okay, so given a document, I would like to discover what is the mixture of topics that enter into this document. Okay, and then there's a second matrix which is about topic word parameters. Okay, so given a topic, I would like to specify what are the likely words that appear in this given topic. Okay, so both of which I assume to be low rank because even though there are many documents, I imagine the number of topics people like to talk about is much lower than the number of documents. Okay, any questions about specification? Yes.
Yeah, I'm just not used to thinking about this. Why is Poisson the right distribution?
It's an easy way to model non-negative integers, and it's only specified by 1 parameter. And also, you can do easy Bayesian update.
Okay, those sort of the mathematical side of the answer. Is there sort of a reason why it's a good fit for what's happening?
You can ask the same question: why Gaussian is used in real value? There's mathematical tractability, but at the same time, it seems to work pretty well. But there are cases in which you might want to make some changes to the distribution. Yeah.
Just a question along this line. For latent dirichlet allocation, they are actually binomial, right?
Yes.
So Poisson is considered a limit when p goes to infinity and number of data points is larger. So does this directly cover LDA? I guess that was.
I think so. Yeah, for special cases LDA. But there are so many work on LDA that I wouldn't just blatantly say that they cover all cases of LDA. All right. So just to give you some more context, we're taking a Bayesian approach. So we're going to assume there's gamma priors over these latent parameters that specify these low rank matrices. What we would like to do is given a specific Bayesian model, how the latent parameters interact with each other in the prior and the observed data, we would like to form a posterior over the latent parameters. Okay, so we'd like to learn what are distributions over the topics, for example, or what are the potential communities that underlie the entire social network. Okay. Right. So one example again is the topic modeling case where for each document we'd like to think about what are the mixture of topics, and each topic is specified by the set of likelihood, the most likely words that appear in the given topic. Okay, so this is just a picture giving you some more context. All right, so this is a data science and privacy workshop. Of course, we'd like to think about what happened, what kind of inference technique we would like to use if the collection of statistics contain sensitive information. Okay, so specifically, what we don't want to happen is once we discover the latent structure, we don't want the latent structure that get published to reveal too much about a specific document or about a specific interaction between pairs of actors. Okay. So this is a motivation, and of course, the way we like to think about a formal privacy guarantee is using differential privacy. Okay, so I'm going to defer the actual formal definition we use in this paper to later. But for this audience, most of us are experts in this field. So the high-level idea is we like to introduce randomness in our computation to ensure that the probability of any outcome remains approximately the same if any single observation and data is changed in an arbitrary manner. Okay. So the actual privacy context we think about is actually a strong variant of differential privacy. We like to think about local differential privacy, which is recently deployed in many organizations. So the way you introduce the randomness into a computation is actually introducing into the data. So before you aggregate the data, I'm going to add noise to the collection of statistics. And then I would like to perform my Bayesian inference on top of the noisy counts. Okay. So this is should not be something you haven't seen before. Okay. So what kind of noise should we add? Okay, so let's think about the kind of data we look at here. The kind of data we have here is basically counts, which is non-negative integers. Okay, so the noise we would like to think about usually Laplace or Gaussian, which is often real value. So it's a bit strange to actually mix in the real value noise with integer counts. But this is an easy problem to fix. So if you're only dealing with integers in your data, there's actually a very easy way to perturb the data using the so-called two-sided geometric mechanism, or the geometric mechanism, which is generating integer noise that kind of look like a discrete Laplace distribution, and you can perturb the data using this kind of the Laplace-like distribution. Okay. Okay. So now the problem is kind of augmented. Okay. So now before what we look at is we assume the true data is generated from some Poisson likelihood distribution, and we'd like to factorize it into some set of low rank with latent matrices. Okay, but now we actually don't get to observe the true data. Okay, what we observe is really the true data added with two-sided geometric noise. Okay, so what's good about this setting still is, even though we don't actually observe the true data, we know how the perturbation takes place. We know the noise parameter in some sense, which is kind of the privacy parameter in the latent privacy mechanism. Okay, so the new goal here, which is different from basic Bayesian inference here, is now suppose your data is being perturbed by some locally private mechanism. How do you actually form posterior over the latent parameters? Okay, any questions so far? Right. So let's revisit this problem, and what would you do in this setting? Okay, so if you think this is thinking about noise, adding noise, perturbing the data is too much work, here's something you might want to try. Like in my actual work, is the so-called naive method. What you do is given this noisy data, you just pretend that the noise was never there. Okay. You have to do a bit extra work because the distribution is two-sided, so you actually may have negative counts. But you could truncate it back to 0 and pretend the noise was never added, and just do standard Poisson factorization. Okay.
When you say incoherent, is that like a technical term, or is it just like a?
I will show more actual plot. This should not be here. Okay. So the question is, can we do better than this naive method? Okay, so we're kind of being ignorant about the noise we added, which should be thought of as part of the data generated process. Okay. So what we would like to do is, we can think about the noise we add from the geometric mechanism as part of the data generated process, and actually take that into account in our Bayesian inference. Okay, so in a way, kind of similar to some prior work by Williamson and McSherry, but they were using this kind of posterior approach to improve the accuracy of query release. So what we would like to do is we want to take both the underlying generated process of the true data into account, along with the noising mechanism for local privacy, which we do know the parameter. Okay, so the question is, can we actually do that? Because it seems a little complicated. We basically augmented the data process with some additional noise, and is it worthwhile the effort to actually do that? Okay. All right. So let's basically revisit what would you have done if there's no noise added. Okay. So there's some standard method for forming posterior given the model and observed data. Okay. So suppose your latent parameter really is given by two matrices theta and phi. Okay. So the standard method is called Markov chain Monte Carlo, or MCMC. What it does is really construct some form of Markov chain. Okay. What you do is you initialize the two parameter theta and phi with some initial value, and iteratively you would do the following. Given the candidate value of the parameter, you sample the other parameter given by this complete conditional on the candidate parameter and the observed data, and then you alternate between them. You will also do the same thing for the other parameters. So you perform this alternate update to keep sampling new parameter given by the conditional distributions. Okay, and what can you say about this MCMC method? If you run this forever, there's some nice math you can do. You can show that it will convert to some stationary distribution, which is the exact posterior. Of course, you never run this forever, but rather you run it long enough, for perhaps 2,000 iterations, and take the last batch of iterates and use that to approximate the underlying posterior distribution. The point is, this is pretty well understood. Without privacy concern, this is typically what people do for Bayesian inference, and it works pretty well. Okay. Now, we don't actually have the luxury to directly apply that. Okay. So what we have here is not just the underlying latent models that generate the true data, but rather we also add noise to the observed data. Right? So the actual data we get is the true data with some added some two-sided geometric noise. Okay. So what we would like to do is actually condition on the noisy data, taking into account that there are the underlying mechanism that generates true data, and also the randomized response method that noise the data. Okay. So we want to do a slightly more complicated posterior inference. Right. So how do you do that? Okay. So I would like to relate this locally private inference with something we know how to do very well, which is the standard MCMC method. Okay. So I'm gonna expand this conditional distribution slightly by introducing the true data kind of as a part of the latent variable. Okay, so I can expand out this conditional distribution by taking an integral over the true data. Okay, given the the observed noisy data, I can I can form a measure over the true data y, and I can take the conditional over conditional on the noisy data over both the latent parameters and the true data. Okay, so this allows us to basically think about another form of MCMC if we introduce the y as part of latent parameters as well. Okay, so what we can do is insert the true data as pretending as if it's a part of latent parameters, and do this kind of sampling from this complete conditionals. Okay. All right. So if we are able to sample the true data given by this conditional distribution, the rest of the sampling inside this Markov chain update is really the same. Okay, so given the true data y, what I would like to do is this is just like a parameter for the latent parameter. I'm going to sample the same set of latent parameters I care about in the same way as in standard MCMC. The challenge here is, given the candidate for theta and phi and the noisy data, how do we sample from the, from this distribution, which generate candidates for the true data? Okay, so does the high-level picture make sense? All right. So, okay, so now we're getting into the harder part, which is, is in hindsight I still think it's a little bit, magical. So what we're gonna do is, we interpret the act of, the noisy mechanism perturbing by, the two-sided geometric noise. Okay. So here's, how we observe the data. Okay. So we're given, certain count statistics, which we assume is generated from certain Poisson distribution with a known mean parameter mu. Okay. And, the privacy mechanism is drawing some noise variable from the two-sided geometric mechanism or two-sided geometric distribution. And here's the y tilde plus minus is what we observe. Okay. So this is, kind of the data generated process we face given the privacy mechanism. Okay. So I'm going to do some changes in how we think about this process. Okay, so here's a useful fact. The two-sided geometric distribution, or any random variable generated from it, can be simulated by the following process. I'm going to draw two geometric noise variable, and then just take the difference of it. This is actually exactly the same distribution as a two-sided geometric mechanism. In fact, that's how you would implement the distribution. Okay, so here's a plot for geometric distribution. Okay, so this is just a slightly different way to rewrite the distribution. All right, so here's another useful fact. Okay, so the underlying observed true data variable is generated from the Poisson distribution. It'd be nice if we translate everything into the Poisson land. Okay, so actually, another way to think about the geometric distribution is basically exponentially randomized Poisson random variable. Okay, what do I mean by that? You can actually generate random variable lambda from the exponential distribution with certain parameter, and the geometric random variable is really just Poisson distribution with this random parameter. Okay, so we can actually rewrite these two, noise you add as some form of Poisson random variable as well. Okay. All right. So let's take one more step. A nice property about the Poisson distribution is if you take any two Poisson random variable together and you add them, it's still a Poisson random variable with the parameters adding up as well. Okay. So you can basically rewrite this process by merging these first two terms. Okay, so these are basically two Poisson random variables. I'm going to replace it by a single Poisson random variable. Okay. Now things can get even simplified because now at the end we really just think of the observed noisy data as the difference between two Poisson random variables, which in a way is has a name for it, which is called the Scalon distribution, and really it's just a name for a difference between two Poisson random variables with mean specified by the two Poisson random variables. Okay. So all right. So what have we done? So we basically rewrite the entire generated process by thinking about the observed data, the observed noisy data, as some random variable generated by some distribution called a Scalon, by directly relating the random variable to the latent parameters. Okay, so we basically somehow sidestep the observed data in some sense, even though it's really in there when we generate the noisy counts. Okay, so now what we would like to do eventually is given this noisy count, and given some candidate of the mean of the Poisson random variable, we generate the true data. Okay, we generate draws from the posterior of the true data. Okay, so how do we do that? Okay, so keep in mind that the mu dv is the true mean of the true data. We're kind of getting there because what we observe is what the noisy counts we observe is actually governed almost by the same random variable. Except that we are actually perturbed by two random variables for which we know the exact distributions. Okay. So for that, I'm gonna go through a small thought experiment. Okay. So This is a bit technical, but it'll be over soon. Okay, so suppose I want to draw two Poisson random variables. Okay, and I'm going to define two quantity associated with these two variables. One is basically the difference between them. Okay, the other is the minimum between these among these two variables. Okay. And we know, the first one is really the the Skelton distribution, which is what we observe. The second one also has a name. It's called the Bayesian distribution. You don't actually need to know that. Okay, but so this is one way to generate the set of four variables. At the same time, I could actually directly generate these two. Okay, by drawing a Skelton variable first, and then drawing a Bayesian distribution, a Bayesian random variable second, which will allow me to actually directly, deterministically reconstruct the two Poisson variable in the first place. Okay, so why would we want to do that? What we have is basically some random variable generated from the Skelton distribution. Okay, but the actual variable we would like to draw, which is the true data, is from this Poisson distribution. So, in the end, we would like to generate the sample from the Poisson distribution using this kind of deterministic relationship. Okay. So why would that be useful? So let me revisit the problem we started with. So we have noisy count, which can be thought of as generated from this Skelton distribution, okay, which is the difference between two Poisson random variables. And we can also define a minimum between these Poisson random variables, which is something drawn from a Bayesian distribution. Okay. So by introducing these two random, latent variables, we can actually sample from them. Okay, we can incorporate them as part of the MCMC Markov chain. Okay. What's nice is that now we can actually recover something that is the sum of the true data count added with the Poisson latent variable, which we know where the distribution is from. Okay, so at the end of the day, one nice fact we will use is that suppose we know the sum of two Poisson random variables is added up to some constant. What we would like to do is draw one of the Poisson random variable. This is really the same as drawing from the binomial distribution. Okay, and this can be efficiently implementable. Okay, so drawing from binomial distribution is much easier than sampling from the Bayesian distribution. Okay, so that was a long tour across many of the distribution and much of the Bayesian math. But at the end of the day, what have we done? So we basically take the two-sided geometric mechanism. We interpreted the noisy mechanism as part of the data generated process, which allow us to actually derive a pretty clean form of how we can generate the true counts as part of a latent parameter. Okay, so this math might look very complicated. At the same time, it's pretty promising because all we rely on is the underlying data is generated from Poisson distribution with unknown parameters. Okay, so this is a very wide class of models, and basically this kind of Bayesian update can actually be applied to all these models as well. Okay, so this is quite nice. Right. So something I've been waving my hands on is how do we formulate the privacy guarantee in this sort of setting? Okay, so one challenge we face for this sort of form of count data is that for example, if I'm given a document represented as word count vector, there's usually no a priori guarantee of how long, how many words the document contains. Okay, so in some sense, to provide the local privacy guarantee, it could be difficult because that in some sense the L1 sensitivity could be very large. Okay, so we're going to twist the definition a bit. Instead of thinking about the indistinguishability among all possible pairs of observations, we only impose it on nearby observations. Okay, so it's a weaker guarantee. And this kind of relaxation also appears in other domains. For example, you might think about financial network where there's large transaction money, but you don't actually want to add noise scaling to the worst case transaction, the amount of transaction you add, and also to location data. Recently, there's the notion profile-based local privacy, which is also a generalization of this guarantee. So in the case of documents, what it means is you might still learn something about the entire document, but you wouldn't know whether some specific set of words or tokens appear in the document at all, provided that the number n is large enough to cover the size of tokens you want to protect. Okay? Yes?
I'm trying to think about the examples you gave. It seems like most of them would do okay with averaging instead of counting, right? If I have a longer document, it doesn't mean that it's related to more subjects, and the same goes for a person that just uses more
perhaps. Network. But I'm not doing averaging here. I'm actually doing local privacy here. If someone sent me a word count vector, I'm going to directly noise it. There's no averaging effect among people. You could think about, maybe you can do better in a more central model.
I mean averaging in the sense of per person, instead of dealing with the counts, dealing with the percentage of the words in the document that were related to a certain subject, or the percentage of his communications that were with a given person, and always have it sum to 1. And then have the n sort of...
I don't think that normalization will actually help you here. If everything is summed to 1, the noise you add is still summed to 1. You're still erasing all of the information.
Right, but then you don't have you don't need to add a different value of noise to a different person. It's just baked into the fact that some of them had more communications that were spread, but still.
So the noise we add will be the same in every person. It should not be, the mechanism should not be depending on the data. Yeah.
So only the guarantee is dependent on n, not the mechanism.
Yeah. So in our case, actually, the mechanism doesn't even depend on n. If I fix a noise weight add to every observation, I actually have this guarantee for any n. But the epsilon just get words for larger n. Okay. Yeah. Your question?
Right, so maybe I'm doing my type checking wrong, but this looks a bit like sort of event level, word level privacy with very small epsilon, with like epsilon set to epsilon over n.
Yeah, it's almost like word level, but maybe like a set of token level, like
right.
maybe
but the
5 tokens.
Small enough so that you allow lots of words to change.
Yeah.
Where lots is n.
Lots is n. Yeah. So here's one example that I came up with last night. I suppose someone sent me an email containing certain contents. Most of the stuff is not sensitive. It's like a proof that someone came up with. But maybe a certain set of keywords are more sensitive. Okay, so what we'd like to do is, maybe I don't actually try to blindly add large amount of noise to protect the entire email or document, but add noise so that certain sensitive keywords would not be rediscovered by looking at it. Okay, so how much time do I have?
15 minutes.
Oh wow. Okay. So I'm gonna just briefly talk about some of the experiments we did for the paper. So one thing I would like to revisit is I talk about this naive method for Bayesian inference given noisy data, which is pretend the noise was never there, but you have to do some small amount of pre-processing. Basically, given the noisy observed data, what you can do is look at some of the negative counts, because add noise that's unbounded, you might actually make some of the counts negative. You can truncate it back to 0, okay? And then just pretend the noise was never added and perform posterior update over the noisy data. Okay, so basically you would like to do better than this naive method. After all, we did a lot more complicated math. So the setting is we're gonna actually generate synthetic data. Okay, so we're gonna generate rather sparse latent matrices of means for the Poisson distribution, and we're gonna print out data given by this distribution. Okay, so this is what the matrices, the heat map of the matrices look like. We're gonna add two-sided geometric mechanism to the data, which will noise the data quite a bit, and some of the counts will be negative. Okay, so what you do by truncating all the negative counts to 0 and do naive posterior update, you get some estimate that look like this. Okay, so. Okay. And our estimate actually, at least visibly look better. At least we can recover the most concentrated block in the matrix, and the more importantly, actually produce a more sparse estimate. Okay, so if we don't actually think about the noise added, the naive posterior estimate actually produce a much denser estimate. Okay. Some toy example will also run by applying it to topic modeling to the state of union addresses. Here's one sample topic. If you just run the standard MCMC method, one topic will include keywords such as year, dollars, billion, physical expenditure, war increase, total estimated. Okay, and if you apply the naive method, you also get similar topic. Actually, for a prefix of them, actually it look pretty reasonable. But later on, as you go down the list of the keywords in this topic, there's some words that by eyeballing you realize this should not be there first place. And our method, seems to do better in terms of recovering this kind of topic model. At least we recover the kind of keywords that should appear when you're talking about spending of the government onto different things. Okay, so we also perform experiments on other real data set. There's this data set called the Enron data set, which is quite nice for our purposes because it covers both the text data case, which is it gives natural text about email content, and also it models how a set of actors interact with each other. Okay, so it also gives a network data set. So one thing we did is we take the data and we would like to use our Bayesian estimate to provide a point estimate for all of the mean parameters, and we would like to calculate the mean absolute error in recovering these latent mean parameters. And our method actually do better, and almost matching the non-private case, and much better than the naive case, because the naive case actually often produce much denser estimates. So many parameters should have been 0 in the first place. The naive method will actually fill in a non-zero value. And there's also a measure of coherence in terms of the topics. I'm not going to go in here. But higher value of coherence means better. So we are also we're beating the naive method as well. Okay, so we also use the same data set for community detection, the problem of community detection. So this N1 data set model roughly a set of people emailing each other, and the private data there is kind of, in some sense, edge privacy. We'd like to protect how many times me and Mark have talked over the last year, up to some precision. So one surprising thing we realized is, this is real data set, so it probably given how the world works, the data may not actually be generated from a Poisson draw of random variable. And our method, our proposed method, actually beat the non-private method in some sense. So this is some surprising effect of actually telling the MCMC algorithm that we are adding noise to the counts and performing inference over them. One thing we do observe, by telling the MCMC algorithm we're adding noise and taking the true data as a part of the latent parameter into the inference, our method actually produces a much sparser estimate of the latent mean parameters. Somehow this actually helps improve the accuracy, because most of the data we deal with are very sparse. Okay, so if you're given a word count document, most of the words will not appear in this document, so most of the entries are 0. So sparsity actually helps improve the accuracy.
So sorry, the non-private version is still the Bayesian method, but just you don't have to worry about the noise?
Yeah. Oh, well, there's no noise added.
Right.
There's no noise added.
But it's still exactly the same Bayesian model.
Yes.
And did you try running your technique on the non-noised data?
Yes, that would be a good thing to try. It could be that we could lie about lie to the MCMC algorithm that
exactly.
We pretend we added noise.
It's probably not lying. The point is probably there is noise, and sort of acknowledging that is.
That's right. So
is useful.
we're kind of in the pipeline investigating that.
Okay.
And maybe relate to your previous question, why is the true counts generated with Poisson distribution? Probably not, but for niceness and mathematical tractability, we use that. But somehow by telling the algorithm there's noise, it helped to overcome some of the overfitting of the Poisson distribution.
So have you run, just forget about the data that you're dealing with here, actually you've ran simulations, you know the exact true distribution.
Yes.
You ran your Bayesian thing and then you ran,
So I'm not showing here, I think if your synthetic data is actually generated from this Poisson distribution, the non-private method would do better in our experiments. Like if everything is generated from the ground truth distribution, where you know the latent parameters, just by adding noise should not improve your accuracy.
Okay, that makes sense. Okay, fine.
Yeah. But this is data, that's real data that we try to fit the Poisson matrix model over.
Have you tried at all smaller values of epsilon over n? Because this is not very strong privacy, so how badly does it break down?
Good question. I don't remember. I can dig it up with a larger experiment. It would deteriorate over time as you increase it.
And if I understand correctly, you're decreasing epsilon as you go.
So,
right?
So you should think of it as we just changing the amount of noise we add, which will get.
Which direction is more noise?
Good question.
It looks like it's going to the right is more noise, but that's not.
I think going to this direction is less noise.
Nice breaks
The
down.
naive method sort of.
Convergent.
Oh yeah.
Better now.
I think we have an explanation in the paper. Let me dig it up.
I guess my question really was, does the red line ever go back up, or is it just get better and better, the less you know?
Well, it depends on how. It could be you actually push it at some point push the algorithm produce sparse estimate. But at some point if you're overly sparse, it should go back up.
Presumably.
Yeah.
So here's a possible explanation of what's happening. So by increasing the amount of noise, and you're actually telling your algorithm that I'm adding more noise, it is integrating out the kind of noise by introducing some kind of regularization.
Yeah, so that was the idea. So the sparsity idea. But it could be overly sparse over time. So it could be maybe answering Adam's question. If you push the regime larger, it could be
you see it go back up. If you
Yeah.
choose epsilon to be small enough.
Yeah.
One question. I have a question. So the fact that adding more noise is giving you less, more accuracy, and what Adam was asking, if you keep increasing the amount of noise, do you see something better? My question is,
not in the extreme.
Do you have confidence intervals for the accuracy as well? Because this is just a simulation experiment, right? So I see some bar there. Is that just a feature of the plot, or is that really a 95% confidence interval for the...
So this is drawing from the posterior, so we don't have confidence interval, but I think
you have
what
a posterior measure.
we have
maybe there's a lot of overlap between the green line and the red lines if you actually look at the posterior confidence intervals rather than looking at the point estimate of the mean absolute.
Yeah, that would be a good idea. Actually, one thing we could do is take the last batch of iterates and see how big a variation is. Good question.
Yeah, I was wondering about how you set n in the experiment.
Oh, so we don't actually need to commit to n. One nice consequence of using the geometric mechanism is, you just need to fix the noise rate. For every possible value n, you get a fixed value epsilon. So we interpret, the privacy guarantee for different n. So it takes a proof. So another thing I would like to mention in the end, one thing that maybe is less satisfying about this work is we actually add noise to the entire count matrix. Okay, so the original data might actually be extremely sparse, as I mentioned, but now we actually have basically a dense matrix with almost every entry being non-zero. So the algorithm actually is much slower compared to the non-private algorithm, where you're dealing with sparse data, so you don't actually explicitly need to write down the entire matrix. We have been doing some ongoing work for doing faster inference. Instead of doing the private MC method, we're trying to incorporate the Bayesian characterization of the posterior to actually do variational inference. Which is kind of like an approximation, kind of algorithm for forming the posterior. You specify a model to approximate posterior, and you optimize over the parameters. And we have some pretty interesting and nice improvement over the runtime. All right. That's it. Thank you.
We have maybe 2 minutes for questions.
Yeah. My question is different. So you have some data, then you add some noise and to keep them private, right?
Yeah.
So the question is, who owns this data, and then who adds this noise on them?
So in the experiments, the data is collected. We pretend it's distributed, but you can think about in a company situation where maybe there's some manager collecting the data, but before the data is collected, the employee actually noise the count. Okay.
Then the company can use the data. And,
yeah. So everything is noise, so you can directly.
Throw it on the ground.
No, I was just going to thank you.
Any last questions? I have actually one question.
Yes.
So you said that you guys started moving to variational methods, but you're already doing a Gibbs sampler with conjugate updates. And my understanding is like the updates probably can be done almost in parallel when it comes time to do the count updates. So that it's got to be amazingly fast already, like I would have thought.
No, so there are some details I'm hiding. For example, sampling from a Bessel distribution actually is very slow. Even though if you do the parallelization, like actually introducing all the latent, auxiliary latent variable and sampling for it is non-trivial.
So then, is it?
If
you just stuck with Metropolis, a Metropolis update, where you don't worry about trying to do a conjugate update. I would assume you're still doing faster than this, though.
You mean the naive method, or?
No. So what I mean is that what you did is you basically worked out the conjugate distribution, right?
Yeah.
So you can do the Gibbs update. However, you never had to do that. You could have just done Metropolis, which basically says the posterior is proportional to.
Yes, that's true.